Hello everyone, this time I'm going to give you a little insight into scaling and optimization and why SpaceX's proposed ITS big Falcon rocket concept has 42 engines. Now of course the exact number of course, there's the joking explanation that it's all a Hitchhiker's Guide to the Galaxy reference, but to actually know why this exact number, you probably have to be involved in the design, but I can tell you why it's something between 40 and 50, or roughly that many, or more than most other rockets. Uh, First of all, of course, 1 or 2 days from now, depending on time zones and how you lay it out, uh, SpaceX will do the first attempt to relaunch a landed and reused rocket. So we're all excited for that, and of course, I'll be watching this too, and possibly talk something about that after that happened, and hopefully succeeded. Probably succeeded. I mean, they did do test firing, they did do all the testing they could. Anyway, on to the actual topic. Now, if you look at the optimization of rocket engines, there's two ways to look at it. There's the optimal way, that is assuming that all the technology is way ahead and all the engineering and machining is basically perfect and 100% reliable. That's the best physical way to build a rocket engine out of the given materials. Of course, that's not exactly how actual rocket engines then are, but you can assume that rocket engines in reality kind of scale to that. And the other way is to actually think about the engineering difficulties, and then you can compare these. Now, if you assume perfect engineering and perfect technology that is not existing yet, then an optimal rocket engine, the smaller the rocket engine, the better the thrust-weight ratio would be. So bundling together many tiny engines would actually give you the optimal system if each engine was 100% reliable and perfectly built and really simple to build, which it isn't. But in theory, since essentially you'd have to, given the same or roughly the same nozzle and combustion chamber geometry, just scaled, you'd have to transfer the force of the thrust, or the force, the lateral force that is equivalent, that is proportional to the thrust over less way. You could have the same engine pressure, and you would have, with the same chamber pressure in a smaller engine, you would have less thrust, but you would have even less weight. It would scale, the thrust would scale roughly squared, and the weight would scale roughly cubed, actually, which is not that oversimplified. Actually, it's actually since the material has to carry the force over less way, so you need less material. So hypothetically speaking, the optimal way to build a rocket would be with an approximately infinite, or a really huge number of tiny engines. It would of course flatten out as the weight of the engines becomes kind of irrelevant compared to the weight of the fuel tank, which you can't really do much about. Now, of course, in praxis, or in reality, there is an engine is actually kind of complex. Obviously, a rocket engine. So you can't build them really small. You can't use too many of them. It's going to become difficult. And the smaller you build an engine, the lower the thrust weight ratio becomes, because of the complexity of the mechanism and the difficulty of the whole turbo pumps and the whole engineering of the plumbing. So while the hypothetical optimal combustion chamber is best at being very small, the practical rocket engine design is best at being as big as possible, and these kind of meet. There's a kind of optimal middle ground, and as technology advances and we learn more and more about rocket engines and we get better and better engineering and better simulations, this optimal middle ground shifts more and more towards the many smaller engines. And that might be one reason why the big Falcon rocket has so many engines, because it is a highly advanced engine that is actually still kind of in development. And it does have a really good thrust-weight ratio. It has the best thrust-weight ratio of any rocket engine ever designed for spaceflight. There are, of course, rocket engines built for things like air-to-air missiles that have a better thrust-weight ratio but are completely impractical to use in spaceflight. And that really great thrust-weight ratio, of course, makes it possible to do a high delta V mission with really few stages, and that's really core to SpaceX's concept of reusability. And so that kind of explains why the Falcon 9 and also the big Falcon rocket concept use many small engines rather than 4 big ones or 1 big one. Now, of course, there are many more interesting points about the new Raptor engine that influence this too. I'm not going to go as much into detail because I've seen other people go really deep into detail on things like the special turbo pump design of the Raptor. Also, a little clarification, the Falcon 9 is actually a rocket with very many rocket engines, and the Falcon 9 Heavy especially. You might think that the Soyuz rocket actually has a lot of engines, but that's actually a misconception. That kind of depends on how you define engine, but if you define engine in a sane way, then the Soyuz rocket only has 5 engines running at takeoff. Each of these engines has 4 nozzles. That's kind of an interesting little trick of early Russian rocket engine design that I might get into in another video. Anyway, it's 1 combustion chamber, 1 engine, 1 turbo pump, 1 system with 4 nozzles, which kind of takes advantage of the smaller nozzle design while keeping the plumbing in 1 part. So that's a really clever design, and the Soyuz engine thus looks like it has 4 times as many engines as it actually has. It actually only takes off with 5 engines, though at first glance you might think it has 20 engines at liftoff, which would be more than the Falcon 9, but that's actually not the case. Anyway, I hope this video was kind of interesting. I'm always open for suggestions, questions, or requests, and thanks for watching.